So during this last hour, we saw how we can use autoencoders to create some useful representations of our data in an unsupervised manner. But this is not something that only autoencoders can do. And now we're going to generalize a bit and think about representation learning in a more broader context than just with autoencoders. So basically the motivation for this is that the kind of features that we use to solve a problem are very important. As a more commonplace example, think about doing algebraic operations like division using Roman numerals instead of the Arabic numbers that we use. So it would be much harder to do it with Roman numerals. In machine learning, we also know that using the right features, the right representation, can make a task much easier to achieve, so to achieve our goals. Deep learning can be seen as a way of stacking feature extractors until the final classification. So if you want, you can imagine a deep neural network as being just a single neuron or a small set of neurons at the end where the classification is made. And everything that is below that, all the millions of weights that you have below that, are only finding the right features for this last neuron to decide whether it's class 1 or class 0 or something like that. So the idea of representation learning is to find the best representations of the data in order to improve learning. For example, if we have limited data, we can have overfitting, but if we learn the best representation, then we can reduce that. And as we saw with autoencoders, good representations can often be learned without labeled data. So instead of using just supervised learning, we can use unsupervised or semi-supervised learning. So if there is a good paper from 2013 from Benju, Corville, and Vincent, which talks about these representations and these meta-priors, these assumptions that we can make about the kind of problems that we're trying to solve. And I'm going to talk about a few of them just briefly, but I recommend that you read the paper because for these parts it has a good overview of these aspects. So one thing is that actual data is not distributed at random over all possible feature values, but actually covers just a small subspace, a manifold of possible feature combinations. And if we can find that subspace and represent it better, we can really improve the way we handle the data. Another thing is that usually features that are relevant are not entangled, are independent factors or nearly independent factors. So you can have the shape of objects, the color of objects, the orientation of the light, and so on. All of those things contribute to the image, but they are independent factors. They are not entangled with one another. There is also a hierarchical organization of factors. So you can, for example, consider patterns that make faces or bodies or hands, but those are formed of simpler shapes, and the shapes are defined by edges and colors and things like that. And you can find a hierarchical organization of these factors. Another important thing is that even though you need labeled data for some part of the problem where you train a classifier or a regression or something like that, unlabeled data is a lot more numerous and still can give us information about structure. So we should try to find these good representations, not merely looking at labeled data, but also taking advantage of the much more numerous and available unlabeled data. There are also shared factors that are important for different problems. So we're going to actually see one example of that with the MNIST and fashion MNIST classification, but you can imagine that many problems in image recognition depend on factors like contrast, edge orientation, and things like that are common for different types of image recognition problems. Another aspect is that often the relevant factors are sparse. For example, suppose that we are classifying animals and we look at whether they have, how many legs they have, whether they have tail, whether they have teeth or wings or feet or things like that. And not all animals will have everything. Each animal will only have some of the features, and they are distinguished because some animals have some features, others have other features. Also, the functions we are trying to learn usually are smooth in the sense that once we train our classifier or whatever, our network, we don't want it to change a lot the output for small differences in the input. So usually small differences in the input will result in small differences in the output. So with these kinds of assumptions that we can make about the data and the problems we're trying to solve, we can see the importance of trying to capture some regularities, because if we can extract useful features from our data, we can make our problems a lot easier to solve. And also we can reuse these relevant features in different problems, reuse these representations, learn these representations from more abundant unlabeled data, and so on. So this is the kind of reasoning, the motivation behind representation learning. And the idea here is to try to find some way of representing the data that helps us proceed and solve our machine learning problems. One historically important approach to this was unsupervised pre-training of individual layers. So this was one initial approach to solve the problem of training deep neural networks. Before good optimizers and before things like rectified linear units, so about 10 years ago, it was very hard to train a deep neural network because of the vanishing gradient problem, and training would stop. So one of the first approaches was to do this greedy layer-wise unsupervised pre-training. It's greedy because it's optimizing each part independently, not looking at the other, doing the best for each layer, and we are pre-training one layer at a time. So basically, imagine that the first layer of your network, you would train it as the hidden layer of an autoencoder, where you input your data, you output after some decoder the same thing as you input, exactly your data, and you are training the first part, just the encoder, to represent the data in some way in your autoencoder. Then you throw away the decoder and you use this encoding as the input for the next layer. So you train another autoencoder, throw away its decoder, and then you start stacking the different autoencoders. If you do that, for example, with noise, by doing denoising autoencoders and stack the denoising autoencoders, you can actually get a pretty good initialization of the network, where at each layer you are finding good representations of the data, and then you just fine-tune everything with backpropagation, but it's already pre-trained and very close to the target where it becomes useful. So this works in general. You can use actually pre-training in general as a kind of regularization. You don't need to do it by stacking, doing it with one layer at a time, because nowadays with rectified linear units and better optimizers, we can easily train a deep neural network. But you can still do pre-training to get your network initialized at some configuration where you have a good representation of the data. And you can use pre-training with unsupervised learning if you do something like an autoencoder to train your net. So the reason why this works is that you force your network during pre-training to reach a different region of the parameter space where it would normally reach if you just started training with your labeled data, for example. This works. It's still used in some cases where you have poor initial representations, where the way of representing data we already know from the start is not very good. For example, in natural language processing, it's often the best or the most common way of representing data like documents is by using one-hot encoding. So you can mark with a value of 1 if the document contains some specific word. And you have one position in your vector for each different type of word you can have in the document. So you can see that it's a very large vector, and if you want to say which word is in one position out of, for example, 10,000 different words, then you only have one value and 9,999 zeros. And then on the other vector, you have 1 and the rest zeros and so on. And this is bad for learning because not only of the large dimension, but also all vectors, all one-hot encoding vectors are equidistant because they all have 1, 1 and the rest is 0. And this is very hard then to deal with this kind of data. But you can do unsupervised pre-training and train word embedding just by looking at documents without labels and learning the structure of these vectors. This one particular example is this human actions data set that has data from sensors and then used to try to distinguish between different actions. So this has a huge number of dimensions because of the different sensors and the time series and so on. And it's 0 most of the time. It's very sparse. But in this example, they started by training with an autoencoder, so the unsupervised pre-training, and then using the representation of the autoencoder and just PCA on that representation, and we could see. Okay, sorry about that. There was some glitch with the PC, but I think it's stable now, I hope. So let's see where I was. Okay, so we were looking at pre-training, and this was an example where using this data set with very high dimensions from sensors to detect human actions. After pre-training with unsupervised pre-training, it was possible to compress this data in fewer dimensions where we could easily see the different clusters of different types of actions for those patterns in the data. So the way this works, we can think of unsupervised pre-training or pre-training in general as a kind of regularization, because we can use pre-training to move the weights of our network, configure our network into some different region of the parameter space where the network is working better than otherwise just random initialization. So this is a paper. You also have this described in your textbook that shows a representation of iterations in your network. So training the network, 50 different networks, and showing the iterations. These are the original vectors are the output of all the neurons in the network. So you see this is very high dimension, but with these manifold projections with TSNE and isomap. So these are methods for visualizing very large dimensional space. TSNE preserves distances between close neighbors, and you can see the structure of layers with pre-training and without pre-training, and you see that without pre-training they tend to diverge more. But in this projection, the large scale distances are distorted, so you're only looking at local regions and how the different networks relate. If we use isomap, which preserves these larger distances a bit better, we can see that with pre-training we squeeze the networks into a different part of the parameter space. So this is without pre-training, with random initialization. This is with unsupervised pre-training. And we can see that now we're exploring a different region of the parameter space and a lot more condensed, a much narrower region. So actually pre-training has this regularizing effect because it's restraining the set of parameters that we have to that smaller region there. So unsupervised pre-training has this historical importance because it was used before we could easily train deep neural networks, and it was used in that greedy layer-wise supervised pre-training method, but it's still used in different applications where we can gain something by using unsupervised learning, using unlabeled data to organize the weights, the parameters in the network better. There are some disadvantages. For example, if you start with unsupervised pre-training and then move to supervised training, you actually may have to adjust your hyperparameters twice, or you may not be able to use the same kind of learning rates and things like that from one stage to the other. However, in some cases, for example, natural language processing, it's very widely used. In the particular case of natural language processing, because we have huge amounts of unlabeled data, it's very easy to collect a large corpus of written texts, but it's much harder to categorize them and label them when we are doing some kind of classification. So unsupervised pre-training to compute embeddings of words for natural language processing is still very common. Another related thing related to this kind of representation learning is the ability to transfer what we learned in one task to a different task. So this may be actually quite different tasks, but they share lower level features. For example, you can have a network trained for handwritten digit recognition, but it still is capturing some kinds of features that maybe you can take advantage of to do image recognition in some other context, or vice versa, use a network trained for image recognition to try to identify handwritten digits or something like that. Because you can have shared lower features like the edges and so on, or you can also have shared higher level representations. For example, for speech recognition, you may need to train parts of your network to distinguish between the way different speakers speak, how their voice sounds, the pitch, and so on. But then all the part of the network that deals with the sentences, the structure of the sentences, the kinds of words that usually come together and so forth, that one is still the same, because if the speakers speak the same language, even though they have different voices and different lower level features, they may have a similar higher level representation of the structure of the language itself. So whenever you have these shared relevant factors, it may be helpful to transfer learning from one task to the other. We may have the same underlying function applied to different domains. So this is a different aspect, the domain adaptation, but it's the same basic idea. For example, you trained a model to detect the kind of sentiment people express in comments, if it's favorable, unfavorable, if they're angry or pleased or something like that, on comments for movies or songs in some database. And now you want to do the same thing, for example, for a grocery store or an electronics shop or something like that. And it can be the same kind of problem, the same kind of underlying problem of detecting sentiment in language, only now the data set is a bit different because you don't have exactly the same kind of data. And this is the kind of examples where unsupervised learning, for example with a deep autoencoder, can help create a common representation of all these examples and then use that representation to train your classifiers. Concept drift is a problem that is similar to adaptation domain and transfer learning and so on. The basic idea is the same, but it happens when there is some gradual change in what you actually need to map. For example, suppose that you have a model that predicts credit risk or something like insurance, something like that, where you look at the features of the people asking for credit or buying some insurance, and you have to predict something about their risks. The relation between the features and what you need to predict may change gradually over time, for example, when the economy changes. So jobs that were very safe and profitable 10 years ago may gradually be becoming more risky or less profitable or such, and you need your model to adapt gradually to those changes. So in those cases, you can still use most of the features, the kind of representations you had previously, but you need to start transferring because the mapping is changing, or because the distribution of the data is changing. For example, if you have a brand that is used by some kind of customers, but it starts becoming popular and then everyone starts using it, the data that you have, the distribution of features on your customers will change over time, and you may need to adapt the model for that. So in these cases, you can still take advantage of most of what was learned before and just use that as some kind of pre-training for your model. So basically the idea here is to use what we learned in different conditions to some new kind of problem. So the common thread is that we reuse what was learned before. Extreme examples can be when you have this one-shot learning and zero-shot learning. So basically you only need one example or even no examples of the new data in order to learn. This may sound a bit weird, but I'll give you an example from this paper from 2013. We have this word manifold created by unsupervised learning. So this is a word embedding which can be done in an unsupervised manner by creating this manifold that represents the closeness between different words. So you can look at many different written texts and see what kind of words appear together, how they are similar, appear in similar contexts, and things like that. So for example, king and queen probably appear close to other types of words that are very similar or the same in the case of king and queen. So you get king and queen in some specific configuration in the embedding that reflects that kind of geometry. And then they use supervised learning to map known images to the words. So this was another part of the system that was trained that could map the image of a horse to the word horse, images of dogs and cats to the word dog and cat, and such. So they are creating, or not dog and cat, so in this case it was just dog for training, for this example, automobile, and so forth. So this learned the kind of manifold for the words, so the manifold of the words, unsupervised, mapping of images to words, supervised, but now you can have a new kind of image, for example, a cat. There was no training with cats, or a truck. There was no training with trucks, but the same kind of mapping that works for all these images that were trained can now map the new image close to where the correct word is. So now the image of a cat comes close to the word cat. And this is an extreme example. They call this zero-shot learning because the system never used cats for training. So this network had no experience with labeled cat images. It just had experience with unlabeled cat words, which it mapped into that manifold, and then labeled images of dogs and horses and so on, which gave the overall map of these different examples, in which the cat image ended up being projected close to the cat words, so the network could label the cat image as a cat, even without having seen cats before. So this is the basic idea of taking advantage of previously trained models, and we're going to do an example today with a small network that you trained in fashionist last week. But if you want to use those large networks that have been trained with millions of examples, you can go to this website, this page for Keras, and you see which networks there are available in Keras that you can download, including the pre-trained weights, and that you can adapt to your problem. So if you have, for example, image recognition problems and so on, you can start with a pre-trained network that was trained with lots of examples, with lots of computation power, a very large, powerful network, but it's already ready to use. So what we can do with this kind of pre-training, we can break down the problems into simpler parts. We can train parts of our network with abundant data, for example, for unsupervised pre-training. With supervised pre-training, we can also break down the model and train different parts of our model, and then add more complexity as we go into different problems and so on. We're going to see an example of that with transfer learning using the neural network, convolutional neural network you created last week. And we're going to use most of that network that was trained with fashionist, and we're going to use that to classify handwritten digits with the MNIST dataset. So the fashionist dataset that we used last week is this one. It has these grayscale images of clothing with 10 different categories, and you created this convolutional neural network to classify these examples. Now we're going to use the pre-trained network that you created last week, most of it, and apply it to the MNIST dataset, the handwritten digits, by just training a small part of the network. So the dense part of the classifier, we're going to train it. We're going to leave all the convolution layers the same, under the premise that the kind of features the convolution layers have learned, which are those edges and orientations and such, will also be useful to classify the handwritten digits. So we'll leave those alone and reuse the pre-trained network. So for today, you're going to create the same model, the same graph of computations. We're going to use the functional Keras interface, not the sequential one, but we're going to create the same model, load the weights that you saved from last week, and then set all the convolutional part to not trainable. So those weights will not be changed during training. And now we're going to create a new dense layer for training with MNIST and just train the dense layer on the output of the convolutional part. So let's see how to do this. We're going to import the Keras from TensorFlow, the optimizers and so on, and we're going to load the MNIST dataset. So last week used the fMNIST, the fashionist dataset. Today we're going to use the MNIST dataset, the one with the handwritten digits. Now there was one small point that I forgot to mention last week. Usually we do standardization because we subtract the mean and we divide by the standard deviation to bring all our features to the same scale. In this case, we already have our pixels all in the same scale. They are grayscale images and the pixels range from 0 to 255. So in this case, it's best to use normalization instead of standardization, and which consists in converting everything into a range of 0, 1. And you can do this easily just by dividing by 255. So you convert all these bytes of grayscale intensity into floating values of 0, between 0 and 1. This is the best way here because if you try to do standardization, some pixels are always black. They have a 0 standard deviation, so you cannot then divide by 0 and it will not give you it will give you problems with the code. But in this case, since everything is at the same scale, you just need to divide by 255. It can probably work without this division, but you may have some problems with convergence. But either way, do this if you did it last week. So if last week for the fashionist you divided by 255, then divide the MNIST dataset by 255. If you did not do this, then don't do it now, because otherwise your previously trained network will not work. So we're going to start by recreating the original architecture, but using the functional API from Carriage. The functional API consists of simply using your layer objects as functions, as callable. So you create this convolution in 2 dimensions, for example, with these parameters, and you call it by giving the inputs as argument. When using the functional API, we usually use this initial object, which is the input constructor in Keras, which just gives us a tensor with the specification that we have here. So we need this because now we're going to chain the different layers together by specifying which tensor is input to the layer as an argument when calling the layer like as if it was a function. So this is the functional API, because these layers are also functions. They are callable, and we can call them with the input tensor. So we create this tensor called inputs, which is using this input class here. And now we create a 2-dimensional convolution layer to which we give the input as argument. And then we put that in a temporary variable that we just keep stacking the different layers. So notice that these are exactly the same layers that you created last week. This is important. You need to have exactly the same architecture in order to load your previous weights. The difference between this and the sequential model is that you're not calling add to add to the sequential model. You are chaining the layers together by giving as argument the previous one. So we create this convolution in 2 dimensions. We give it this tensor as input. It outputs a new tensor, which we call layer. We give this tensor as input to the rectified linear unit activation. We store it again in this variable. We give it as input to batch normalization, and so on. And we chain together all these different layers. Now, the reason we're doing this exactly the same way as we did last week is so that now we can compile our model. We use whatever optimizer. It doesn't matter, because this one will not learn anything. And we load the weights from what we saved last week. So here you load the weights file that you saved from last week. One small detail here: when you reach this flattened part, so remember from last week we had the convolution layers here, and then eventually we would step on to the dense part of the network. And before we did this, we would have to flatten the multidimensional tensors that come from the convolution parts into a single one-dimensional tensor. So we use flatten here. In this case, we're going to give a name to this layer. We're going to name it features, because it's the one we're going to use for the network we're going to train. And we're going to also call the first one the input tensor. So this way we can easily identify these 2 layers in our model, and then stitch everything together with the new model that we're going to create. So this part here just recreates the last week's model that you trained for fashionist and loads the weights. And then we have this important part here, which is for each layer in our old model, last week's model, we are going to set this trainable flag to false. This means that these layers will not be trained. Their weights are fixed, are frozen, and they will not be changed during training. Now we're going to build the new layer. We're going to create a dense layer, a new one, which receives as input the old model here. So we're going to create a dense layer with 512 neurons. And notice that we are using this constructor as a callable. So this is also the functional API. And we are giving as argument the tensor being output from the input layer, from the features layer, sorry, of our old model. So our old model, if you recall, has all these convolution layers, and then it flattens everything out, and we call these the features layer, because these were the learned features from the convolutional part. And now we create a new model that branches off from there. So our original model would continue with its own dense layers and so on, but our new model just picks up from this features layer and applies an activation, batch normalization, dropout, this dense layer with 10 neurons for the softmax classification and such. And now we're going to create our model by starting from the input layer of the old model. So all the way back here, this one was the one we called inputs. This one feeds into the convolution layers and so on, all this way, and then it ends up in this flattened layer here, which we called features, but which we continued in our new model. So the flattened layer comes here in this part of the graph, and it continues with these new layers. These new layers are trainable. The ones from the old model are not, because we deactivated the training flag. So now we create a new model that starts with the inputs from the old model and ends with this last output in our new model. And basically what we're doing here is we're taking all the convolutional parts of the old model, which we froze. They will not be trained anymore. And these will just serve to just be used to produce features for the dense part of our new model. And now our new model will be trained in the MNIST dataset. So basically we create the optimizer, we set the parameters, we compile our new model here, and now we fit it with the MNIST dataset. And this one is using the frozen layers from the convolutional part of last week's model and just training the last part, the dense layer at the end. So you can do this in only 5 epochs. I think that maybe 1 or 2 you already get about 98% accuracy on the validation. But if you train the one from last week properly, then this one will be very easy to train. And you can even compare. You can now create the whole model from the start and train everything from the start if you want, and compare the two cases. So another exercise that you're going to do is dimension reduction with an autoencoder. This is the UCI banknote example I gave a few times already. You can create an autoencoder. You can pick your own architecture, for example, the 642 that I showed before, or 1682, something like this. You can then just train the autoencoder. So you create all these dense layers and you train with, for example, mean squared error to minimize the difference between the input and the output. So remember that since these are continuous values here, you can use mean squared error and the linear output for the 4 final neurons that will output the same values as the input for this data set. And after training, you can take the activation from the hidden layers. So basically, you train your autoencoder, but you have this encoded part here. You can create a functional model where the encoded part is just for the first part of the encoder. So you create the whole model, but you can call one of the layers the encoded layer when you create your model, and this is the layer that corresponds to these 2 neurons here. So from your original model, you can create a new one that has the same input, but the output is that internal layer and not the output of the whole autoencoder. So basically, you have one neural network, but you create 2 models. The first one for training, where the output is the end of the autoencoder, and the second one for prediction, where the output is the output of this innermost layer in the autoencoder. So I'm not going to detail this very much, because the idea is that you look at the model, look at the functional API, and think a bit how you can do this. But the main focus of this exercise is to get you started with the functional API so that you can do these more sophisticated manipulations of your models where you can use part of the model or reuse part of the model and so on. So from this, you can also compare with the principal component analysis and do this kind of plot where you compare your manifold representation of the data with principal component analysis. So just a few bureaucratic notes. Note that next week we will not have classes because of the Easter break, but the test will be as planned on the 16th. So, well, not quite as planned. It will be at the date and time as planned, but it will be online, not in person. And I still don't know exactly how it will be, but the idea is that you will have a web page where you have the questions. You will have 4 questions, 15 minutes for each one, and you send the answers by email to that address that I use for the assignments and so on. Note that one problem with online testing is that it's very easy for students to share their answers with one another. So I'll try to design the test with that in mind, and the assessment will be mostly focused on how clear your answers are, your reasoning, how good the explanations and so on. So basically those things that are not easy to just copy when you look at someone else's answer. The test will be provisional because I think it will go all right, and this is 4th year. It's not the same as with 1st year students, so I think this will work and there will not be a problem. But I may request some oral grade defenses from some of you, maybe with a random sample or something like that. Or if I see that all the answers are the same, then I may have to discard the test, and then we'll see how we can do the assessment if the test doesn't work. So I still don't know if this is going to work. I am confident that we can make this work if we all cooperate, and in any case I'm going to try to make the test in a way that even if you share the answers between yourselves, it will not make much of a difference, and you should be more focused on trying to answer instead of reading other people's answers. So that will be the idea, and the test will be on the 16th at 6 o'clock, so at the time of the tutorial. I'll try to update the lecture notes during this week. Download today's versions for the tutorial because it has this part of the fashionista and so on, but the theoretical part is still very incomplete. I will try to update them, and even though we don't have classes next week, I'm still available by email, so use the mailing list or email me directly if you have questions to study for the test. And by the end of next week, maybe on Friday or Thursday, regardless of the holiday, I'm going to do a sort of rehearsal for the test so that you can check how the thing will work online, all the mechanism of the pages and emails and so on. And I will let you know on the mailing list when I get this set up. And this will be voluntary. You don't need to participate, but this is just to help you out, to take a look on what to expect when you do the test, which I still cannot give you much details because I'm still implementing this, but by the end of next week you should have some version to try out. So to sum up, this is the end of this first part of the course, so this first half. For this lecture, for representation learning, the basic idea is this motivation of improving learning by having good representations of the data. So you can see pre-training, for example, as regularization, as shifting the network in parameter space towards more promising regions. There are some historical important aspects in unsupervised pre-training, but it's also a good thing when you can have that kind of data, because learning good representations is always helpful, not only for solving a particular problem, but also for transferring learning into other different problems. So I recommend that you read chapter 15 of the textbook. And also there is this section here, 8.74, but mostly chapter 15. And also this is an interesting paper you can I can give you as a recommendation as an additional learning, because it really structures these kinds of aspects, of foundational aspects for representation learning. So that's it for now. This today I took a bit longer. Sorry about that glitch a while ago. I don't know what happened, but things just froze in one of the computers here. But we'll meet back again at the Hangout, say at 6:15. Let's take a 10 minutes break, and we'll meet at Hangout again.